All right, let's begin on this section on compound probability. So first we have to talk about something called a compound event. So what is a compound event? A compound event is actually two or more events, kind of like a compound word. It's two or more things that we would consider at the same time. So for example, someone might want to know what's the probability of a die landing on a 5 and having a coin land on heads at the same time. Or like what's the probability of Bellwood Annis's golf team winning the next 2 matches in a row. Normally it's one thing and then another thing. And sometimes they're in succession, sometimes they're kind of separate. But before we can really get into how we find the probability of those things, we need to talk about something called the sample space. So a sample space, there we go. A sample space is basically a list of all the possibilities that could occur. So if we flipped one coin, we would get heads or tails. If we flipped 2 coins, it could be heads, heads. It could be tails, tails. It could be heads, tails, or it could be tails, heads. See how there's 4 different options: heads, heads, tails, tails, heads, tails, or tails, heads. Of those 4 possibilities, you might want to know, like, what's the probability of getting heads twice in a row? Well, that only happened 1 time out of the 4 possibilities, so 1/4. Listing all of the options, though, can kind of get pretty confusing when there's more than 2 possibilities. One way we can express all of those different possibilities is by creating a tree diagram. A tree diagram shows the first choice kind of like here. It's like there's heads or there's tails. And they're like, oh, well, I could get heads and then heads again, or I could get heads and then tails. I could get tails and then heads, or I could get tails and then tails. And then at the end of each tree diagram, you'd list all of your different possibilities, all the different paths that led there. So let's look at this example and actually create one. It says create a tree diagram showing all the possibilities of spinning the spinner and flipping the coin. So let's spin the spinner first. So we're starting with nothing. If we spun the spinner, there are 4 different options that we could have happen. We could land on blue. We could land on, I'm calling that red. It's kind of like orangish. We could land on, I'm calling that yellow in the bottom right. Or we could land on green. And after we do that, we're going to flip the coin. And we could land on blue and get heads. I'm just going to put an H. Or we could land on blue and get tails. We could land on red and get heads. We could land on red and get tails. We could land on yellow and get heads. Land on yellow and get tails. Land on green and get heads. Or land on green and get tails. So total, in the end, I would write all of my options. I could call this BH for blue and then heads, BT for blue and tails, RH for red and heads, RT, red and tails, YH, yellow heads, boy, my handwriting's bad, YT, yellow and tails, GH for green and heads, and GT for green and tails. So total, there were 8 possibilities. I found out that there were 8 possibilities by listing them all. You might notice, though, the number of possibilities that we have is really just the how many possibilities. Hold on, I'm going to read that again. You may notice the number of possibilities each individual event possesses can help us find the number of possibilities a compound event had. So we had 4 possibilities for the spinner. We had 2 possibilities for the coin, and we ended up with 8 different outcomes. What we really do is we just multiply them together. 4 times 2, there's 8 different options. We actually call that thing the fundamental counting principle. I honestly forget that name a lot of times. I just know you multiply them. So let's look at this example. Ginger can choose between wearing a black, white, or blue pants. Okay, so there's 3 options for pants. With a red, blue, green, or yellow shirt. Okay, so 4 options for shirts. How many different outcomes are there? Okay, well, we could list them. We could be like, okay, so I can wear black pants with a red, a blue, a green, or a yellow. And I could do that again for white. I would have 1, 2, 3, 4 options. And then blue, I'm sorry, black, white, or blue. I better write black and blue so I don't have 2 B's. And you could be like, oh, there's 12 different things here. 1, 2, 2, 2. Cool. You can count them all if you want. Or if you want to kind of step up your game a little, you could just be like, oh, okay, let's just take 3 times 4. So in the end, 3 times 4 equals 12 options. That's called the fundamental counting principle, which I need to remember. So let's look at some questions about this stuff. Number 1, which is not a compound event? A, shooting a shot in basketball, then shooting another shot. No, that is a compound event because that's 2 different events, either in sequence or at the same time. Letter B, drawing a marble from a bag and randomly selecting a student. That's 2 things happening at once. That is definitely a compound event. And then C, randomly selecting 2 popsicle sticks at the same time. So because it's the same time and you're doing the same thing, that one really wouldn't count. It's not one and then another. You're doing it at the same time. And it's the same event. Do you see how the other two are different? This one's same event, but different times. These two things are different events. C is just kind of doing the same thing at once. You're picking two things. It's not one and then the other. Okay, number 2. List all the possible outcomes that could make up the sample space of rolling a 6-sided die and spinning the spinner below. Okay, so let's actually list them this way. So I'm going to start with the spinner first. So with the spinner, and then I'm going to write die over here. I could have the spinner land on a 1 and then the die land on a 1. Spinner land on a 1 and then 2, 1 and then 3. See here I'm going 4, 5, 6. And then I could go 2, 1, 2, 2, 2, 3. And see how this is like a sick game? The easier way, it's sick no matter what. We can use a tree diagram and just go like this at least. 1, 2, 3, 4. That's for the spinner. And then we could go 1, 2, 1, 2, 3, 4, 5, 6. Why did I make this question? This is like 3, 4, 5, 6. So difficult to cram in here. What is wrong with me? I don't even think that's 6 things. 1, 2, 3, 4, 5. Yeah, I didn't even make a 6th branch. Let me say this. This is not how you should make them. Don't be like me. Give yourself 4, 5, 6. Give yourself enough room so that way you can list them all. Like, they always should be even. Like, see how this one's higher and this one's lower? Do not do that, okay? Don't be like me. But I listed all the options. You could be like 1, 1. You could write it like 1, 1, 1, 2. Man, this was terrible. Okay. Anyways, though, that's what you would do. Number 3, sketch a tree diagram showing the sample space of flipping a coin 3 times in a row. Okay, so first flip is heads or tails. Actually, let's learn from our last mistake. Oh, Barry's crying because he realized we screwed up last time. You're right, Barry. So we could have heads or tails. I gave myself more room. And then from there, I could have heads or tails. That's flip number 2. Or if I got tails, maybe I could get tails, heads, or tails, tails. And then I could have a third flip. Heads, tails, heads, tails. Barry wants attention. But you know what, Barry? You're going to have to wait. Sorry, buddy. And I should list all the possibilities. Like I should write like heads, 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 tails, heads, tails, heads, heads, tails, 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 heads, heads. You can barely even see this. Tails, heads, tails, 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 heads, and tails, tails, tails. 8 different options there. Number 4, Vanessa's trying to get better at upcycling and wants to make her own dress. She can choose from 15 different materials for dresses, 4 different stitch patterns, and 16 different styles. How many possible dresses could she make? I am definitely not going to try to make a tree diagram. I am just going to multiply those up thanks to the good old fundamental counting principle. So 15, I'm using a calculator. 15 times 4 times 16 is 960 possibilities. Man, I'll tell you what, all these problems are fine except number 2. I hated that question. Okay, number 4. So compound probability. So we just found out how do you find how many total number of events. Now let's find how to figure out compound probability. So compound probability is where we're trying to figure out the probability of a compound event. 2 things happening in a row, or 2 things happening at the same time. And what we're going to do is we multiply each individual probability together. So in doing this, we have to be careful to recognize whether the events we're considering are either independent events. So we can't just straight up multiply. It is tempting. So we have to consider if our events are called independent events, which means they don't affect each other. So for example, flipping a coin and spinning a spinner. If I flip a coin, that doesn't impact at all what the spinner is going to do. Or dependent events. And Barry's still upset. Like, for example, if I draw a card from a deck and it's like a 3, well, now there's one less 3 in the deck to choose from. So, like, if you're hoping for a 3-2, well, now your odds of getting a 3 are changing because of what I did. So when it says an example of each is shown below, let's read this one. Vance and Lexi show up at a party when Lexi asks how good the cookies look. Vance grabs a random one from the tray, so he gets one, then he puts it back, but decides to grab another random cookie for himself. What's the probability that he grabbed a chocolate chip cookie both times? These are independent events. So let's look at the first one. So I'm going to write first, and then I'm going to write second cookie. Okay, so the first cookie. What's the probability that was chocolate chip? Okay, there are 3 chocolate chip cookies out of 1, 2, 3, 4, 5, 6, 7, 8 cookies. So he grabs it. So there used to be 8 cookies. Now there's only 7 cookies, but hold on. He puts it back. So there's actually 8 cookies there still. And because he put it back, it's like you might think, oh, there's only 2 chocolate chip cookies. He put it back. Well, nope, joke's on you. There are still 3 chocolate chip cookies because he put it back. So I would take 3 out of 8 times 3 out of 8. The probability that he randomly got a chocolate chip cookie for both would be 9 out of 64, which 9 divided by 64 is approximately 0.14, about 14% of the time. So that's going to be different than this situation. What if instead he grabs a cookie for Lexi and then gets a second cookie for himself, but he doesn't replace it. He just straight up takes it. So let's look at this. The first cookie and then the second cookie. So the first cookie, if he grabs a chocolate chip, there's only 3 of chocolate chips out of 8 cookies. Now, here's where it gets different. He grabs a cookie for Lexi, and then he goes back to get one for himself. Well, there's not 8 cookies anymore. He took one of them. So it's almost like, let's imagine this chocolate chip cookie is gone. Okay, he took one. There are now only 7 cookies left. Of those 7 cookies, he took a chocolate chip cookie. There are no longer 3 chocolate chip cookies left. There are only 2 left. So this is what I have to multiply now. You can see this is called dependent. Independent events, you still have the same kind of total. Dependent, things are changing. And dependent is more tricky. So I just need to multiply these. I'm going to cross simplify. 2 goes into 8 4 times. 2 goes into 2 1 time. Multiply straight across. You get 3 out of 28. I don't know what that is, though. 3 divided by 28 is approximately 0.11. So about, man, that squiggly is bad. About, I gotta stop saying squiggly. That approximate symbol is bad. About 11% of the time, that would happen. See the difference in the percentages, too? Between those two? Okay, as you can see, probabilities change based on whether the events impact each other. Again, if they do impact each other, that's called dependent, because one will depend on the other. If they don't impact each other, that's called independent. So let's look at this example. London's on-base average for softball is .364. Lily's on-base average is .021, and Chloe's is .246. If each girl isn't impacted by the other, what's the probability that all 3 girls get on base in a row? So they are not impacted. That means they're independent events. If they're independent, we just find the probabilities and multiply them because one isn't going to change the other. So I just take 364 times 0.246. Oh, I need to get them in order. I got to get it together. So 364 times 0.271 times 0.246. These are the 3 things I'm multiplying together. Again, I can do it because they're independent events. They do not impact each other. So if I multiply those, it should be kind of unlikely to have 3 hits in a row. In the end, when I multiply these, I get about 0.023. I mean, that's about a 2.3% chance that it happens. Yeah, that's not that common. And if you ever watch like a baseball or softball game for 3 players in a row to get a hit, I mean, it can happen, but it's not like insanely often. Let's read some of these questions and wrap this up. So, number 1, which of the following is a pair of dependent events? That means that one will impact the other. So, A, rolling a die and spinning a spinner? No, those don't impact each other. B, drawing a deck from the card, then drawing another card? Yes, that actually was the example that I used. That will impact the other. And then, letter C, bowling one frame, then bowling a second frame. Well, if it was just like one time up and then you finish the frame, that would matter. But if you bowl a frame in bowling, that's like you get 2 chances. They actually reset the pins. So no, you'd still have 10 pins to go from. So no, that actually would not impact each other. Number 2, the probability a warehouse light bulb gives out is 0.04. Each light bulb's lifespan isn't affected by the others. Okay, I'm basically saying here, these are independent. What's the probability that 3 light bulbs burn out? Well, the probability of 1 is 0.04, so that's for the first light bulb. The second light bulb, the probability that it burns out is 0.04. And for the third light bulb, the probability that it burns out is 0.04. So what do you think we're going to do? Well, we just multiply them together because they're independent. They don't impact each other at all. So I can just multiply them. So 0.04 times 0.04 times 0.04 gives us this number. Oops. I need to have it ready. 0.123464. That's a probability. Super low. That'd be 0.006%. Number 3, your grandma tells you a story about how her mother ended up having 5 daughters and ends the story by saying, what are the odds? Although it's meant to be a hypothetical question, you choose the answer anyways. Way to go. What are the odds? Okay, well, the probability that the first one's a daughter is 0.4. You've got a 50% chance of it being a girl. The second one, I said 0.4 and I wrote 0.5. It's 0.5. The probability the second one is also 0.5. The third one is also 0.5. The fourth one is also 0.5. And the fifth one is also 0.5. We could also write this, by the way, like this, 0.5 to the fifth. But either way, if we calculate this, we find that this answer is approximately 0.03. So the odds that you have 5 daughters in a row is really 3%. And you could do this for anything. My grandpa actually had 7 brothers, so 8 boys. You could calculate the odds by taking 0.5 times 8. Or raised to the 8th, I'm sorry, not times 8. Number 4, Charlie's eating dinosaur-shaped egg candy, and like every sane human knows the green ones are the best. Got that right. If he wants to save them for the end, what's the probability the next 2 candies he randomly grabs aren't green? Okay, so let's do first candy and second candy. He's grabbing 2 candies. The probability that the first one is not green, well, there's 1, 2, 3, 4, 5, 6, 7, 8 candies, and of those, 6 of them are not green. Okay? So then, assuming he grabs one that's not green, there are now only 7 candies to choose from. He's taken one. He's taken one of the not green ones. I'm going to cross out this one as a sacrifice. So there's only 7 left. Of those 7, only, 1, 2, 3, 4, 5 of them are not green. Right? Because we still have 2 that are green. So we would multiply those together, 30 over 56. I don't know what that is, but if I type in my calculator, 30 divided by 56 is approximately 0.54. So about 54% of the time, he would grab ones that aren't green, which I occasionally do when I eat gummies, but I typically try to save the green for last. So hopefully that helps. That should be the end of this section. If you have any questions, let me know.